Lecture 13, Part A, on energy density, pressure, and buoyancy. Examples of energy density. For a tangible example of an energy density or an energy per volume, drop a gallon of milk on your foot. As it falls, the gallon of milk changes the potential energy into kinetic energy. Just the same as a ball or any object we've been discussing, as it falls, it increases the kinetic energy. When it comes to fluids, the topic of this week, we don't talk about the particle of water or the particle of milk or the particle of whatever the fluid is. We talk about the volume of fluid. So it's more practical to discuss the energy of a volume of fluid rather than the energy of particles of fluid. So we're talking about the gravitational potential energy of a volume of a fluid, such as the gravitational energy of a gallon or a liter of milk. As it falls, it transfers itself into kinetic energy for the gallon or liter, for the volume. After it hits your foot, the gravitational energy per gallon or per liter or per the volume gets converted ultimately to thermal energy for this volume. Those are examples of a change of energy density. We use them in the same way that we've been discussing all semester for the changes of energies, except now we focus on volumes. Here we're talking about volumes of water going over, say, a waterfall. Again, changing gravitational energy as it's falling, converting it into kinetic energy as it's falling faster, and smacking into the rocks, becoming thermal energy from the sound, the increase in temperature, the noise, the splashing, the whirlpools, etc., are all thermal energy for particular volumes of fluid. Or we see again our milk gallons. Those volumes, those 4 gallons, start out with high gravitational energy. Then they fall down the waterfall. So it's change of gravitational energy per gallon going into kinetic energy as it's falling, gaining speed as it's falling, going through the river. And then as it hits the rocks and makes noise and sound, becomes thermal energy for the liter, gallon, or volume we're interested in. So when we talk about volumes, energy per volume, we're talking about energy density. So refamiliarize yourself with volume and density. Our symbol for density is the symbol rho. It's not a P, it's the Greek letter rho. In physics, we mean it for the mass density or the mass per volume. Gravitational energy, PE, per volume, therefore, can be rearranged as mgy, the usual potential energy, divided by the volume. But since mass per volume is rho, density, gravitational energy density is rho gy. So gravitational energy density, or PE density, is equal to rho gy. This is the form you'll be familiar with, though we will often write it as in this section. Continuing to refamiliarize yourself with densities. A cubic centimeter means a cube of 1 centimeter on one side by 1 centimeter by 1 centimeter. That's also known, a cubic centimeter of water fills a volume that's the same as 1 milliliter, where a cubic centimeter is also written as 1 cc. A cube that's 10 centimeters on a side is 1,000 cubic centimeters, 10 by 10 by 10, which is 1 liter, since a 1,000 cubic centimeter is the same thing as 1,000 milliliters, which therefore must be a liter. So a liter is composed of 1,000 milliliters and 1,000 cubic centimeters. The density of water is 1 gram per cubic centimeter, or 1 gram per milliliter. Thus, if density of water is 1 gram per milliliter, and 1,000 milliliters is a liter, then 1,000 grams per 1,000 milliliters is the density of water also, 1 kilogram per 1 liter. A cube of water used to be the old standard kilogram, 1 liter. The barometer, a measure of pressures in a fluid. Barometers are used to measure ambient, outside atmospheric pressure. We see in these illustrations a fluid open to the environment, open to the outside. The fluid is being pressed up inside a cylinder from the higher pressures inside versus outside. The barometer is measuring the difference in pressure from point 2 to the pressure at point 1, which is at the surface of the liquid in contact with the outside pressure. The change in pressure, delta P, between P2 and P1 is what's causing the fluid in the cylinder, in the upside down cylinder, to rise up to a height h, or a height delta y. The fluid is being pressed up in the barometer. It's being pressed up because P2 is at a higher pressure than the zero pressure of the vacuum at the top of the fluid. So the difference in pressure is the energy density that's lifting up the potential energy of the volume of fluid. So the change in pressure, therefore, is equal to the change in gravitational energy density, PE per volume, or rho g delta y, where delta y is the height that the fluid is being lifted up. It's the pressure that's lifting up, that's increasing the gravitational energy density of the liquid. So the difference between the pressure at the top of the fluid, which is 0, down to the pressure at the bottom of the fluid, P2, is the difference in pressure delta P, which we said is equal to rho g delta y. So if you measure delta y, the height of the barometer, the height of the fluid, delta y, the height you measure, times it by g, times it by the density of the fluid, in this case water, then you have the pressure, P2, at the bottom of the barometer, the bottom of the column of fluid. But P2 and P1 are the same, because at the same level. So P1 is equal to P2, and P1 is 1 atmosphere. That's the outside pressure. So the outside pressure, atmospheric pressure at P1, has to be the same at P2 since they're at the same level. So P2 is 1 atmosphere of pressure. So what you're measuring is the outside pressure, what the atmospheric pressure is, by the height of the column of fluid. That's what a barometer is. If the density of the material is not that of water, let's say the density of is mercury in the second illustration, then the same difference in pressure from no air or vacuum down to the bottom of the column, which is at the same pressure as the outside atmospheric pressure, will lift up a column of mercury 760 millimeters. So delta Y would be 760 millimeters if the fluid is the density of mercury. 1 atmosphere of pressure, the ordinary outside pressure, lifts mercury up 760 millimeters. If the pressure outside is greater than 1 atmosphere, greater than usual pressure, the column gets lifted up higher than 760 millimeters. This is how we measure the pressure, the ambient pressure, the outside pressure, the atmospheric pressure. This is how the barometer works. The density of water below we see is 1,000 kilograms per meter cubed. Density of seawater is a little bit greater than that. The density of mercury, which we would use in the barometer for the last example, is 13,600 kilograms per meter cubed. So it's 13.6 times more dense, therefore gets lifted up 13.6 times less than a column of water under the equivalent pressure. So a water barometer would get lifted up 13.6 times higher than a mercury barometer. Our standard unit for pressure, our SI unit, or MKS unit that we'll use in this class, is known as the Pascal. 101,300 pascals, or 101.3 kilopascals, or the equivalent of 1 atmosphere of pressure. 1 atmosphere of pressure is a common notation, but is not an SI unit. 1 atmosphere is equal to 101,300 pascals, where a pascal is a Newton per meter squared. Other examples are, as we saw, 760 millimeters of mercury is the same as 1 atmosphere, or 760 millimeters of mercury is the same as 101,300 kilopascals. About 30 inches is the same as 760 millimeters, or pounds per square inch psi, 14.7. The one we most commonly use will be 1 atmosphere and 101,300 pascals. Given this, here's a gas in a container. The gas container is connected to a liquid in a tube. The tube is rising up in the vertical, the liquid is rising up in the vertical part of the tube to a height h. The liquid is mercury. The pressure in the gas is pressing up the mercury to a certain height. So the gas in the cylinder is at a pressure of 3 times 10 to the 5th, or 300,000 pascals, roughly 3 atmospheres. Therefore, how high is the column of mercury? Well, this gas at 3 atmospheres, or 300,000 pascals, is pressing up the mercury to be a certain height. So the change in pressure from the gas along the dotted line, the pressure of the gas at the bottom of the pressure of the gas where it connects to the mercury is the same along the dotted line as the bottom of the column of mercury, where it's the same level as the pressure of the gas. So fluids at the same level have the same pressure. So the pressure of the gas is the same as the pressure of the fluid at the bottom of the column of H. The difference in pressure of the gas lifting up that mercury, increasing its gravitational energy, Pe. So change in pressure goes rho g delta y, where rho is the density of the mercury, and delta y is the height of the mercury has been lifted by the difference in pressure between the bottom at that height of that column, which is the same as the pressure of the gas, to the top. And the change in pressure at the top is open to the atmosphere, so it's 1 atmosphere versus 3 atmospheres. The column of mercury at the top is open to 1 atmosphere, 100,000 pascals roughly, and the pressure of the gas that's lifting it up is 300,000 pascals. So the difference is 200,000 pascals has lifted up mercury of the density 13,600 to the height delta y. So delta P is known, difference between the pressure of the gas and the outside pressure of 101,000 pascals. The density is known, G is known. The only thing that has to be solved for is the delta y with this equation. So the P top, which is an atmosphere, minus P gas is what's lifting it up. Everything is known except for delta y. Again, you measure the height to figure out the pressures. Measuring the height is determined by the height difference is determined by the pressure difference. So again, it's acting as a barometer. Another example of pressure differences is buoyancy. Here we see a container filled with water to the brim. I'm going to put, this cup is filled to the brim. I'm going to put this circular object, this ball, into the cup. So the ball goes into the cup, and naturally water gets displaced, spills out. So water spills out to the spillover container. How much water spilled out? The same volume of water, the volume of water that spilled out is the same volume as the ball that was placed into it. The ball displaced an equal volume of liquid. If we weigh the volume of liquid displaced, that is what's known as the buoyant force. The missing water, the water that was displaced, is the buoyant force that's on the ball. In other words, if the ball wasn't there, that missing displaced water was sitting in equilibrium. Pressures beneath the water before it was displaced were holding it up against its own weight. So the weight of the displaced water was being held up by the water where it used to be, the water below where it used to be. So the buoyant force is simply the pressures on the water below the displaced water. Displaced water was balanced by its own weight, So the buoyant force is equal to the weight of the displaced water. So the equation at the top, the buoyant force, Fb, is equal to the mass of fluid displaced times gravity. It's equal to the weight of missing water, which was sitting in equilibrium before the ball displaced it. We can change mass to density times volume, so mg becomes rho g volume. The buoyant force is the weight of the water displaced. It's not the weight of the object. The buoyant force is pushing on the object the same way I would pushed on the displaced fluid to keep it in balance. So the object that's displacing the missing water has forces on it from all sides. But there's more forces below than above because pressure increases with depth. So the greater pressure beneath the object versus up top means there's more pressure beneath, so the object is pressed up from the greater pressure beneath. It's forced up. The difference in forces from down and up, resulting from the difference in pressure, is the buoyant force. The greater pressure below gives us a net force up, which is the buoyant force. That greater pressure below would press up a weight of displaced water for that water to be in balance. It would hold up that volume of water in equilibrium. Instead, it's pressing up on an object. So to derive the buoyancy force, we have a cylinder here. P1, pressure at top, P2, pressure at bottom, H, the height of the cylinder. We know that pressure increases with depth, so the top and bottom face will have different pressures. P1 versus P2. And that difference is delta P1 versus 2, which is equal to rho times G times H. Since pressure is force per area, and there's more pressure on the bottom face, that means there's more pushing up. Thus, this net upward force holds the water from sinking when equilibrium, if it's simply a volume of water. It forces up the weight. If the cylinder is empty like an air bubble, and the greater pressure at the bottom buoys up the cylinder to the top, because the difference in pressure causes an imbalance or net force upward. The buoyant force is always trying to buoy up the object, to either make it weigh less, to keep it in equilibrium under its own weight, if it's simply the same water, or pushing up on an object that has a density that's less than water. So since pressure is force per area, and force is weight per area, and rearranging a weight per volume times it by a volume per area, meaning volume divided by volume equals 1, so weight per area times it by volume over volume is weight per volume times volume per area. Weight divided by volume is a weight density. So weight density times volume per area, well, that numerator, weight density times volume, is the buoyant force. That's mg v divided by the area. So it's rho, weight per volume is rho g v, which is mg, the buoyant force. Again, it's simply due to the differences in pressure from top on bottom. The difference in pressure would hold up that volume of liquid, but if that volume has been displaced, that difference in pressure creates a force on an object, where the force is equal to the weight of the displaced water. So the force is the weight of the water displaced, not the weight of the object. And the object has the same difference in pressure, delta P, at any depth. Why? Because the buoyant force only depends on the shape, depends on the height, or the height of the object. Difference in pressure is what's creating the buoyant force. So the further the object goes, the further the object is submerged, the deeper it is. It's always the same height. It's always the same difference in pressure, creating the same buoyancy force from its volume. An example, we're looking at an iceberg. How much of the tip of the iceberg is above the water? Well, on our iceberg here, the force diagram, there's a force of the earth on the iceberg, its weight. And if the iceberg is floating, well, there's a force of the buoyancy force, the difference in pressure between top and bottom, force of the buoyant force on the iceberg, equal to the missing weight of the water that is displaced. If you submerge the iceberg, the buoyancy force would be greater until eventually the force is balanced when it's equilibrium, when it floats. The buoyancy force, again, is rho GV, density of liquid, times the volume of displaced fluid. The buoyant force is equal to the weight of the iceberg. So rho GV is equal to mg. And thus we can have, rearranging from mass to be density times volume, and canceling out the g's, the gravitational acceleration, we have an equivalency between density and volume, the density of the liquid displaced, the volume of the liquid displaced, times the density of the object, the ice, and the volume of the iceberg. But the volume of the iceberg is not equal to the volume of the liquid. More of the iceberg, some of the iceberg is above the surface. But we rearrange to see that the ratio of the volumes is inversely related to the ratio of the densities. Thus, if we know the density of the object and the density of the liquid, we know the ratio of the volumes of the object to the liquid, and therefore how much the volume of the object has to be submerged. The amount of the volume of the object that has to be submerged is equal to the density of the object relative to the density of the fluid. So if an iceberg is 90% submerged, it's because the ice is 90% as dense as the water. Sea creatures are very familiar with buoyancy. This tortoise is being pulled down by the force of the earth by its own weight, and it's the buoyancy force up on the creature that can lift it up if it so chooses. How can it change the buoyancy force so it can float at different levels? Well, the buoyancy force depends on the amount of water displaced, on the volume of the object. So the creature increases its volume or decreases its volume, makes itself bigger or smaller to create more of a buoyancy force, to get itself buoyed up or lowered down. Just like expanding your chest, taking in air, or releasing when you're trying to float or sink. Let's do another example. Here we see a ball in the illustration being held down by a tension in a string. A ball weighing 1 Newton has a density 1/3 of that of water. What is the tension in the string when the ball is held underwater as shown? Well, the forces on this ball, there's the weight of the ball, the tension pulling down, and the only upwards force is the buoyancy force. But we're just told the weight of the ball is 1/3 the weight displaced. Its density is 1/3 that of water. The ball is submerged, displacing water, so it's displacing a volume of water that is greater than its own density. So if it's 1/3 the density of water, it's displacing a volume. It's displacing a mass where it's only 1/3 of that mass. So the weight of the ball is 1/3 the weight displaced, 1/3 the weight of the missing water. Since the buoyancy force is the weight displaced, then the weight of the ball is 1/3 the buoyancy force. So therefore, substituting into our force equation, 1/3 the buoyancy force plus tension is equal to buoyancy force. Therefore, the tension has to be 2/3 the buoyancy force, which makes sense. The object is 1/3 as dense as water, and it's displacing water, so the tension must compensate for this light ball to be held underneath the water.